For a long time, we pictured the universe right after the Big Bang as a relatively quiet place, an expanding, dark expanse of cooling, pooling gas. According to our standard models, that early gas slowly coalesced to form the very first stars, which eventually burned out and collapsed into small black holes. This timeline tracks the expected growth rate of those objects. For small black holes to merge and grow into supermassive ones, it should take a gradual upward curve spanning billions of years. To test these assumptions and map out the dark universe, the European Space Agency launched the Euclid Space Telescope. But Euclid just dropped a massive data point at the 670 million year mark, a fully formed supermassive black hole powering a quasar. This single object shines with the light of roughly 1 trillion suns. At this stage of cosmic history, the universe had barely begun building basic galaxies. It is mathematically impossible under our current models for a monster of this size to already exist. Euclid isn't looking at a giant star. It is observing a highly active galactic nucleus, known as a quasar. A quasar forms when enormous amounts of surrounding gas and dust spiral inward toward a central supermassive black hole. As this material falls into the dark void, intense friction heats the gas to extreme temperatures. The center becomes so brilliant it outshines all the other stars in its host galaxy combined. This extreme brightness turns quasars into cosmic beacons, allowing us to detect early black holes across the vast distance of the young universe. Finding them is a needle in a haystack problem for scientists. From our perspective, the faint light of a 13 billion-year-old quasar is perfectly camouflaged by the dense stars of our own Milky Way galaxy. Astronomers cut through this visual noise using redshift. As light travels across an expanding universe, its wavelength physically stretches out. Euclid recorded 2 light waves stretched deep into the red spectrum, with redshift values of 7.77 and 7.69, indicating a travel time of more than 13 billion years. Narrow-focus telescopes struggle to find these distant targets, but Euclid was designed with a wide-field scanning capability to search enormous swaths of the sky all at once. In just a single year, that approach allowed scientists to identify 31 ancient quasars, more than doubling the known population of these objects. This massive dataset proves that these impossibly fast-growing monsters were a widespread feature of the early universe, rather than isolated anomalies. These discoveries effectively dismantle the idea of a slow, gradual dawn to the universe. The early cosmos was vastly more chaotic and efficient, capable of extreme growth spurts that challenged traditional physics. Astrophysicists now have to fix the broken timeline by investigating radical new theories, like massive clouds of gas collapsing directly into dark voids, or black holes feeding at hyper-rapid rates. Inside the European Space Operations Center, teams are actively processing the daily influx of Euclid data to ground these new theoretical models in hard evidence. Solving this mystery helps us piece together the history of our own cosmic neighborhood, including the supermassive black hole at the center of the Milky Way. Observing these quasars means watching the universe's first monsters awaken, revealing how the foundations of all modern galaxies were built.